Dear students, in this class, the basic antenna parameters will be discussed. Antenna parameters can be broadly classified as radiation pattern, gain, directivity, effective aperture, radiation resistance, bandwidth, beam width, input impedance, antenna noise, temperature. Radiation pattern. Radiation pattern can be defined as a mathematical function or a graphical representation of the radiation characteristics of the antenna measured as a function of spatial coordinates. It is normally determined in the far field region and is represented as function of directional coordinates in space, that is r, theta and phi. So, a radiation pattern in three-dimensional form can be viewed to consist of radiation to be maximum in a particular direction and minimum in other directions. This pattern you call it as directional pattern. Accordingly, we can have the radiation pattern defined for three basic structures of the antenna or three basic forms of the antenna. One being isotropic radiation pattern, second omnidirectional pattern, third directional pattern. In isotropic radiation pattern, in both vertical and horizontal directions of observation, there will be equal radiation in all directions. The locus traced by the electric field lines is going to be a circle both in the vertical and horizontal directions of measurement. This isotropic radiation pattern is an ideal antenna radiation pattern. Second, omnidirectional pattern. In omnidirectional pattern, along one directional, the radiation pattern is going to be a figure of 8, whereas in other direction it is going to trace a circle. The third one is directional pattern. In directional pattern, one direction is going to have maximum radiation, while remaining all other directions will have minimum radiation. So, the radiation pattern can be viewed as a three-dimensional structure in space. This radiation pattern can be put in two forms. One is a field pattern, other is power pattern. Field pattern is normally represented as linear scale as a plot of magnitude of electric or magnetic field as a function of angular spatial coordinates, that is theta and phi. Power pattern in linear scale gives a plot of square of the magnitude of electric or magnetic field as a function of spatial coordinates theta and phi. Power pattern can also be given in dB as the magnitude of electric or magnetic fields represented in decibels as a function of angular space. So, the radiation pattern and amplitude radiation pattern can be given as En of theta comma phi ratio E of theta comma phi divided by maximum of theta comma phi, where En of theta comma phi is the normalized field pattern of the antenna. It contains both amplitude field pattern as well as the phase field pattern. In amplitude power pattern, you will have a graph of spatial variation of the power density along a constant radius. In two-dimensional view, it contains a main lobe followed by side lobes on either side with respect to the main lobe. The amplitude power pattern can be represented in normalized form as Pn of theta comma phi equal to P of theta comma phi divided by P of theta comma phi max. This radiation pattern is usually a far field pattern and its field intensity decreases with increasing distance, that is as 1 by r, whereas the power density of the radiated power decreases as 1 by r square, that is square of your radial distance. The pattern, that is the radiation pattern or the shape, is usually independent of the distance in the far field. Radiation pattern can be shown in form of various lobes present in the pattern representation. The lobes are major lobes and minor lobes, where the minor lobes consist of side lobes and back lobes. Together with that, we have the null directions of null, followed by the measurements within the major lobe taken as half power beam width or 3 dB beam width and beam width between the first null or first null beam width. So, the three-dimensional view of a radiation pattern will contain a major lobe or the main lobe with minor lobes consisting of side lobe and back lobe. Side lobe and back lobe. The minor lobes consist of side lobes in the direction of your main lobe and back lobes in the direction opposite to the main lobe. And nulls are the directions of minimum radiation or zero radiation. So here two different classifications of the radiation pattern are shown. One is three-dimensional pattern, other is a two-dimensional pattern. In two-dimensional pattern, you can observe the back lobes and side lobes are present on either side of your major lobe. So major lobe is the region around the direction of maximum radiation, which is usually the region that is within the 3 dB of the peak of the main lobe. The main beam is centered at 90 degrees in this diagram. Okay, main beam. So direction of maximum radiation is 90 degrees here and 270 degrees down. Coming to side lobes, the side lobes are smaller beams that are away from the main beam. See here, these are all the side lobes. These side lobes are usually present in undesired directions which can never be completely eliminated in design. In this diagram, the side lobes occur at roughly 45 degrees. See here, roughly 45 degrees and 135 degrees. Next is half power beam width. This is the angular separation in which the magnitude of the radiation pattern decreases by 50% or 3 dB from the peak of the main beam. From the figure, the pattern decreases to 3 dB at 77.7 degrees and 102.3 degrees. So half power beam width for this particular diagram is 102.3 minus 77.7 is 24.6 degrees. So this angular separation, angle between these two lines or points is 24.6. First null beam width or FNBW. This is the angular separation from which the magnitude of the radiation pattern decreases to 0 away from the main beam. That is, the pattern goes to 0 or infinity, minus infinity at 60 degrees and 120 degrees in the diagram. You can see in this diagram, the null directions exist at 120 degrees and 60 degrees. Side lobes. Side lobes give the maximum value away from the main beam. So, the side lobe is a part of minor lobe and here the side lobes exist at minus 14.5 dB. Next parameter of antenna interest is the directivity. This is the fundamental antenna parameter which shows the ability of an antenna to focus the radiation in a particular direction. By definition, we can define this directivity as the ratio of radiation intensity in a given direction from the antenna to the radiation intensity averaged over all directions. So mathematically, it is D is equal to P of theta comma phi maximum value divided by average of P of theta comma phi. In terms of effective aperture, it is 4 pi into AE by lambda square. An isotropic antenna which radiates equally in all directions has D value equal to 1 always, or directivity of isotropic antenna is 0 dB. Next parameter is the gain. Gain of the antenna is ability of the antenna to convert the input power into radio waves in a particular direction. Though the directivity and the gain describe the same directional properties, the relation between the gain and the directivity is G is equal to K into D. Kg, that is the efficiency factor of the antenna, which lies between 0 and 1. G is lower than D due to ohmic losses in the antenna, that is I squared R loss. Known the property like the gain and directivity being the same kind of parameter description, we have to understand what is the significance of the gain. Often the manufacturers of the antenna specify the antenna gain, whether it be a Wi-Fi antenna or GPS antenna or TV antennas. For instance, the manufacturers of Wi-Fi antenna may market the Wi-Fi antenna as high gain antenna, which is more expensive than a similar low gain antenna. So we have to decide, do we really require a high gain antenna? The answer is, it depends. If you know exactly where your desired signal is coming from, you would like to have a maximum gain direction towards the desired direction. However, if you do not know where the desired signal is coming from, then it is better to purchase or get a low gain antenna instead of a costlier high gain Wi-Fi antenna. Second example to make you understand is TV antennas. If you mount a TV antenna on your roof and know the TV broadcast antennas are to the south, that is, the signals from where you get the TV signals broadcast is from the south, then it is preferred to have a high gain antenna. You need to collect the signals from the extreme south, right, which may be some hill region of your city. So then naturally you need a high gain antenna in order to collect the radiations from the antenna, transmitting antenna. Antenna with a gain of at least 12 to 15 dB is required to collect these kind of radiations. Second example is your GPS antenna, global positioning system. These antennas are used for mobile devices for receiving purpose. The job of the GPS antenna is to triangulate your position by measuring the received signal from multiple GPS satellites. These GPS satellites may be in different directions related to the receiving antenna. So in this kind of GPS systems, you need a high directional antenna. May not be preferable. You need to go for low gain antennas only. Okay, so high directional antenna is not preferred at all for GPS positioning systems. Whereas coming to mobile cellular antennas, the cellular antenna on your smartphone is an example of mobile cellular antennas which communicates with a single cellular network tower. Can have the cellular antenna in any orientation. It can be in any position related to the network tower. So in such cases, it is better to prefer a low gain antenna for our application. Normally, the gain is specified in three different forms. One is dB, other is dBi, other is dBd. dB is decibels, which means if you say 10 dB, it is 10 times the energy related to an isotropic antenna in the peak direction of radiation. Next is dBi, decibels relative to an isotropic antenna. If you say 3 dBi, then it is twice the power relative to isotropic antenna in the peak direction. Third is dBd, decibels relative to a dipole antenna. That is, a half power dipole antenna with a gain of 2.15 dBi can be said to have 7.85 dBd higher than that of a dipole antenna. That is 10 dB higher than the isotropic antenna. It is 10 times higher than an isotropic antenna. So this class I have introduced the radiation, how radiation can be defined, the definitions of directivity and significance of the gain. In the coming class, let us discuss the remaining antenna parameters like your antenna aperture, antenna radiation resistance, noise temperature, beam width, bandwidth, etc. Thank you.